The paper I'm going to present is backed by Bidirectional Autoregressive Diffusion for text-to-motion generation. The main purpose of our paper is to generate motion sequences given text prompts. Our model is able also to do temporal editing tasks like inpainting and outpainting, and also one of the important application of our framework is long sequence motion generation, where we input multiple text prompts to our model and it is able to generate a long motion sequence which is consistent with the input text prompts. The main purpose of our work is to address key limitations in autoregressive models and mask-based generative models. In autoregressive models, we use a causal attention mask in order to determine the causal dependency between input tokens. This causality makes the model to learn the sequential relationships between input tokens in the sequence very well. However, because of this causality, our model cannot learn the bidirectional relationships between our input tokens. On the other hand, mask-based generative models, which are also known as absorbing diffusion or mask diffusion, uses a bidirectional attention mask during training. This bidirectional attention mask enables the model to learn the bidirectional relationship and patterns in the input sequence. So one of the advantages of this bidirectional attention mask compared to the causal attention mask is that our model can learn the bidirectional context from our sequence. However, because of this bidirectional attention mask, the model assumes token independence during prediction because there is no causality dependency between input tokens or mask tokens during prediction. Additionally, mask-based generative models use only a single mask token in order to mask or crop the input sequence. For example, here in this example, if our input sequence has a length of 6 and we mask or cropped 50% of the input sequence, we get something like this. And if we completely mask the input sequence, we get something like this. This corruption procedure is somewhat unnatural and distorts the sequence. So it may complicate the task of learning the corresponding noise to data mapping. In order to address these issues, we propose to use multiple mask tokens. For example, if we have a sequence of length 6, we use 6 different mask tokens. In this example, if we want to mask 50% of the input sequence, we use 3 different mask tokens. And if we want to completely mask the input sequence, we use 6 different mask tokens. However, if we use the same order over and over again for our mask tokens, this is identical to positional embedding. So we propose to use permutation operation to determine the order of mask tokens. So we first sample a random ordering using the permutation operation to determine the order of mask tokens. And then based on this random ordering that we got, we create a permuted causal attention mask. This permuted causal attention mask determines the causal dependency among mask tokens. Additionally, because a portion of our input sequence is unmasked, we create a bidirectional attention mask, which this bidirectional attention mask enables that all token can attend to the unmasked part of the input sequence. So by summing up the permuted causal attention mask and the bidirectional attention mask, we get hybrid attention mask. This hybrid attention mask enables the model to learn the bidirectional relationships in input tokens, and also at the same time it enables mask tokens to learn the causality between one another. Here we show two different hybrid attention masks. Here Z represents the random ordering that we sampled, and here T represents time steps. C is our condition, for example, the text. For example, the text embedding, and here E is the end token. And the blue colors represents the unmasked tokens, and the gray color represents the masked tokens. And for example, here we can see that the third mask token can only attend to itself, and the mask tokens greater than itself, and also the unmasked tokens. And also here we can see that the ninth mask token can only attend to itself and unmasked tokens, and the ninth mask token cannot attend to mask tokens smaller than itself. And also here we show this hybrid attention mask for another random ordering, which is completely different from our time step. And here we also see that the third mask token can only attend to itself, and mask tokens greater than itself and unmasked tokens. So using this hybrid attention mask, our model is able to learn the bidirectional relationship between input tokens, and also at the same time to learn the causal relationship between mask tokens. The overall framework for our text motion generation consists of two stages. In the first stage, we train a VQVAE, which converts raw motion sequences into discrete tokens. This VQVAE consists of an encoder and a decoder. The encoder converts the raw motion sequences into latent embeddings, and then we discretize these latent embeddings, and then we input these discrete tokens into the decoder, and the decoder has to reconstruct the original motion sequence. Then in the second stage, we train a transformer, and this transformer has to learn these discrete tokens. At the beginning of the first stage, which we have our motion tokens, our original motion tokens, we first corrupt our original motion sequence using multiple mask tokens from our mask book and the permutation operation. And then we input the corrupted input to our transformer. And also we input the text prompt into the clip model, and we get word embeddings and sentence embeddings from the clip model, and we apply sentence embeddings and word embeddings to the transformer, and the transformer has to reconstruct the original motion sequence. The objective function for training the transformer is here, and the first term, which is for mask tokens, ensures that the mask token at the position of z of p can only attend to mask tokens greater than itself. So this is a causal dependency for mask tokens, and also the mask tokens can attend to the unmasked part of the sequence. And for tokens that are not masked, they can attend to unmasked part of the sequence. So this objective function ensures that our model can learn the bidirectional relationship from our unmasked tokens, and also masked tokens learn the causal dependency between one another. For generating a motion sequence based on a text prompt, we can use different methods. The first method is the traditional confidence-based sampling, which we first sample a random ordering to determine the order of masked tokens, and we build our completely masked motion sequence, which is our noise, and at each iteration we want to decode these mask tokens, and we pick the one that has the highest probability and keep other masked. So at each iteration, we decode the mask tokens that has the highest probability until all mask tokens are decoded and we get our motion sequence. The first method that we propose is order agnostic autoregressive sampling. In this method, we first sample a random ordering to determine the order of mask tokens and to create our permuted causal attention mask. For example, here we show two different hybrid attention masks. The first row shows a hybrid attention mask where the random ordering happens to be exactly like our time steps. And then we autoregressively decode these mask tokens. For example, the first mask token, which can attend to all other mask tokens, is decoded, and then the second mask token, which can attend to itself and all other mask tokens, and also the unmasked tokens, is also decoded. And at each iteration, we autoregressively decode these mask tokens until all mask tokens are decoded and we generate a motion sequence. Here we compare our model with previous works. Our model, which is an integration of mask-based generative models and autoregressive models, outperform previous works. For example, MMM is a mask-based generative model, and T2M-GPT is an autoregressive model, and our model, which is an integration of these two type of pre-training strategies, can consistently outperform these two types of pre-training strategies. And also because our framework is based on mask-based generative models, which can do parallel decoding, it generates motion sequences very fast, which is very close to MMM, which is a completely mask generative, mask-based generative model. And also, it gets a very good FID. Here we show some generated motion sequences using our BAD framework. For example, here we show that our model is able to generate a natural and coherent motion sequence based on this text prompt. On the other hand, previous works like MoMask cannot generate a natural motion sequence. And also here we show more generated motion sequences.